So what I'm talking about today is modeling quantum registers. And actually also classical variables within the same theoretical framework. So in order to understand why there's even a need for some theory of it, let me give you just some examples of things. I mean, let me first tell you what a quantum register is, and let me contrast it with a classical variable. So let me maybe, to illustrate, write the same program, the same thing in kind of two different ways. So maybe I have a quantum program which says on variable or register Q, apply, for example, Hadamard. We might have an operation like that, and then it may say on Q and R, apply C naught. And similarly, we could also draw a quantum circuit, which would say, and the same thing would be written in this form here. And well, both things are essentially the same. The quantum circuit is actually a small kind of program. The advantage of the quantum circuit is that it's more easy to grasp visually. The disadvantage is, as soon as we want to do things like loops or if then else, the graphical formulation will become, I mean, it's not even clear how to draw it. And if we try, then it's probably going to be rather hard to read. So in this setting, we have Q and R, and they are quantum registers. And usually, when one treats something like this, what one just says is, assume a quantum system, which is a, so let's say our whole system is described by a Hilbert space that is of the form HQ tensor HR. And for example, this might be, I don't know, 5 qubits. And this might be, for example, 7 qubits. And then it's kind of clear what it means to apply H to Q. So the first operation would just mean this is H tensor identity. And then this one is just C naught on the whole system. Or if we would have one more register, let's say S, then this one would be H tensor identity, and this one would be C naught tensor identity. So it seems pretty clear what a quantum register is. A quantum register is just when we write down our space as a tensor product of separate registers, then a quantum register is just one of those factors. Now, there are a number of difficulties with this approach that are usually just blurred over by kind of assuming that everyone knows what should be done. Because, for example, if I have something like this, this is a C naught on SQ. Well, formally, C naught is just a matrix that can be applied to a system of 2 qubits. So if I want to actually describe what this thing does, I will need, so if I want to actually write down the formal meaning of this thing, it would be something like, first I swap those 2 gates down there. So it's identity tensor swap. Then I swap these 2, I think. I mean, I may even be getting it wrong, but that just serves to illustrate my purpose. Then I do a C naught, and then I do those things backward again to bring things into the order where they should be. So applying some gate to a subset of registers is actually a rather fiddlesome thing to do if we use this approach, and especially if we are really precise and we don't we look at the tensor product, and actually the tensor product is depending on how we have formalized it, not even an associative thing. So we would have something like this, which is not the same as putting the parentheses like this, it's just isomorphic. And then in this thing, we would also need to insert additional matrices that are transforming between, that are moving the parentheses around in the tensor product and so on. So it becomes really ugly and cumbersome. Of course, we might ask, can we do it differently? Maybe we can just write down this space H with a different formula in which it becomes clearer what it means to apply it to a subset of the to a part of the register and so on. So maybe it's just like a bunch of qubits, and each register refers to a subset of the qubits. So a register would be modeled as a list of qubits, and then but then we still need to do some transformation of indices when we say we apply it to bits 5 and 7 and so on. So all this, when you really get down to it and want to be precise about it, is rather cumbersome. And I haven't seen any approach that manages to make it really elegant. So especially when we look at formal verification in theorem provers. So for example, we have Yantja here in the audience, who was co-author on some Isabelle formalization of quantum Hall logic. There I looked at it, and it's also like you have these like variables, a list of dimensions, and then there are various operations that transform back and forward. So it's all really cumbersome. And that is just when we want to simply say what a Wolf has a question, yeah?
Did you ever consider Petri nets?
No.
I think this would be a nice approach. I thought about the same problem, and I thought, why don't they use Petri nets? And I think Petri nets have some parallel to Hall logic. I've seen some similarities. So
I'm not sure that it would help here. I mean, my approach is very different, at least.
Okay.
But besides this, let me tell a few more problems we have with registers before I come to solutions. Because we might do the following also. So for example, we had on QR apply C0. Now we have another annoying thing. So we have Q and R. So we need to define what it means to apply something to two registers. But why can't we just say that QR is just one register, just a bigger one? Again, when we are being informal, this is something people happily do. They may say, well, we treat QR together as one register. Or you may say, I would like Q1, the first qubit of Q. I want this to be a register. And again, if you have written your space in this form here, it's suddenly that now I have a tensor product, and now one of these factors I see again as a tensor product, and you get all these explicit conversions back and forth without ever having actually said what a quantum register is. And it gets even worse. For example, sometimes people may say something like Q in the diagonal basis. So they take an existing register and look at it in a transformed basis. Is Q in the diagonal basis the same thing, like the same abstract concept as Q? Or is it something completely different? Or is it just some notational convention, which just means every time you want to do that, you need to basis transform Q, then do your operation, and then transform back. So all of this can, of course, be solved, but I feel that all these approaches of transforming back and forth, and whenever you write some register, of coming up with a sequence of transformations that allows you to work on that specific register, they all feel rather ad hoc, and they don't answer the question what a register is. Because intuitively, a register is just part of a quantum system, no matter in what way this quantum system would be written down, whether it's written down as a tensor product or in some other form. So far I've just put a lot of confusion there. But let me add even some more confusion by telling you that even in the classical setting, it's not clear what a variable is, because the quantum register is the quantum analog to a variable. So consider the following program. X is assigned 5. Seems clear what this does. It takes the part X of the overall memory and puts the number 5 into it. But we could also have something like this. Could have xy is assigned 5, 6. Again, it seems clear what this means. It means we take 5, put it in x, we take 6, put it in y. But now we are already in the situation that we have somehow a special treatment for tuples here. So instead of just saying we can assign 5, 6 to the variable xy, we have a special treatment for this. Would be much nicer if we could say, which is in a sense true, that xy together is also part of the memory, i.e. a variable. But no definition of variables that I'm aware of actually would allow us to say that this is a variable. This is 2 variables. But why are 2 variables just put together not also a variable, just stored in where one half is stored in one place and the other in another place in the memory? So all these things led me to the question, how can I model this? Because even with the classical variables, I found it actually quite tedious to operate them. And for example, if x is of parts term, I might say like x1. In pseudocode, people do that. They say, I assign 5 to the first half of x. Can I do this formally? Not really, normally, because x1 is not a variable. So I cannot put it on the left-hand side of such an assignment. So these are the kinds of things that I encountered. And coming up with a definition of what a variable is, or what a quantum register is, actually turned out to be really difficult. But fortunately, it turns out there's a quite simple solution, a general approach that works both for quantum registers and for classical variables, and maybe also for other computational models that I haven't explored. So are there any questions about the difficulties we are facing here? Okay, so now let me start to tell you how I will actually, how we can formalize what a register is, and how we can then actually see that all the things that I described above are actually just elementary constructions on registers, and we can we get one unified framework for writing all those things. Okay. And I will just in parallel develop both the theory of registers in general and the specific instantiation in the quantum setting. I will skip the instantiation in the classical setting, but it also is possible. So the quantum case will be both an example, but also one of the main motivations on its own. So when we think of registers, we ask ourselves, what is the purpose of a register, both in the classical and in the quantum setting? Well, the purpose of a register is that it tells us it is something we can modify. And when we modify it, it modifies the memory of the whole system. Yeah, so when we write in a register, this implies writing into the overall memory. If we apply a unitary to a register, it implies applying a unitary to the overall system, and so on. So the first thing we need to specify when we talk about registers is what is an update. So if we are in the generic setting, we cannot say concretely what an update is, because in the classical situation, an update might be, for example, a deterministic function that is applied to the register. In the quantum setting, it might be unitary transformation. So in the generic setting, the updates are just a monoid. Why? Because for any given variable, you can perform updates. You can, on the type of the variable, you can chain updates. So you can perform one update, another, which corresponds to multiplication in the monoid, and you would have things like associativity and so on. You have the operation of not doing anything to your variable. So you have an identity, and then you basically get the laws of a monoid. So whatever updates are, they have the structure of a monoid, but in the generic setting, we say nothing beyond that. So more precisely, we have a category with monoids as objects. So why do we have a whole category? Well, we may have registers of different types. So for example, we have register of type qubit. So there we have the monoid of operations on a single qubit. Or we have a register of type 5 qubits, and now we have the monoid of operations on 5 qubits. So basically, for each type of variable, we have a set of operations that you can do on variables of that type, and those form a monoid. So for every type, we have a monoid of operations, and for simplicity, I will just say this monoid is the type of the variable. So what does that mean concretely in the quantum setting? It is just the linear operations from some Hilbert space HA to the same Hilbert space HA. So for every Hilbert space, so any variable has a corresponding Hilbert space, and the set of operations is the linear operations on that Hilbert space. So I just write bold A on it, and I can't do boldface, so I just write A. So the updates on a particular variable are just linear operations. You may ask, why not unitaries? Because it doesn't make sense if I say I update this variable by multiplying its state with 2 times the identity or something like this. Well, we could also restrict ourselves to unitaries, but then there are other reasons why we might need projectors and so on. So it turns out easiest to just say we just put all linear operations there, and later we need to make sure that we have the special cases like unitaries and so on handled. Okay, so defining a monoid of updates is how we define the type of a register. But now, what is a register? Well, as we said, we can apply an update to a given variable, and applying an update to a given variable or a given register tells us how the overall memory should be updated. So a register, and first I will say pre-register, because actually it turns out we need a two-step approach, is something that takes it's a function that takes A, which is some update monoid. So the updates on that variable, and maps them to B, which is the updates on the program state. What does that mean? Maybe I should illustrate it with an example. So let's say our maybe I write the letter M here, because like for the whole memory. Let's say our program has a 7-qubit state. Say further that A refers to qubits 1 and 2. Then, or let's say F. Our register is now called F. No, I used Q earlier. So let me just use what I used earlier. So Q is now a register referring to qubits 2 and 1 and 2. So if I say something like on Q, apply some unitary U, this corresponds to on the whole memory, apply U tensor I5, so identity on 5 qubits. And this means that our register Q maps an update on 2 qubits to an update on 7 qubits by this formula. And from this we can read off what this register would be formulated as a register on our modeling. It would be a function that goes from the set of updates on 2 qubits. So these are the 4 times 4 matrices. It maps it to the set of updates on 7 qubits. So that would be 2 to the 7 times 2 to the 7 matrices. And what it does is it takes any operation U and maps it to U tensor I5. Of course, I've omitted here things like parentheses of the tensor product and so on, but it's just to get the idea. So this is just a special case. So what would it be in the general setting to say we update we perform an update to a register. It has to be mapped to an update on the whole thing, and therefore our pre-registers in the quantum setting are just functions from they are linear functions between the update monoids. So the formalism is again very simple. Any register you have to describe by saying how an update on the individual on the register is mapped to an update on the whole memory. Yeah. But so far, this does not give us much of a theory. So far, I mean, if I describe to you a register, for example, here I gave you the description of what Q does, then you can use it. You can, for example, if I now say on Q apply U, you know what it does, because on Q, no, maybe not there, maybe here on the side, because on Q apply U is now nothing else semantically than just taking Q of U and applying it to the whole memory. So by specifying a register in this form here, we get a very simple mechanism for writing down the semantics of programs like this. But the problem is, we can also write down completely nonsensical registers. So for example, I could write down some register that takes Q and okay, let me go back here, maybe. So a bad register would be something like Q tilde, which maps U to 3U. That doesn't make any sense, because it would mean that if I apply a quantum operator, a unitary on something, it's not a unitary on the whole system. So one first thing I might have to say, might try to say is, well, registers always have to map unitaries to unitaries. And that's already useful. But what if, for example, so another thing that could happen would be, let's say, if I apply U times V, and so I apply first U, then V to the register, and this is not the same as applying both U and V to the register together should be the same as applying U to the register and V to the register. So this would also be an example of something that is bad. So we need to somehow restrict the set of all registers to a set of registers that somehow makes sense. But so far, are there any questions about this modeling of registers? Okay. And another thing that we also don't have an answer to in this modeling is what would be, for example, Q and R together as one register. Okay, if I have two functions that produce, if I know how to map an update on Q and an update on R, do I then know how to map an update on Q and R together into an update of the memory? No, not really. So these are the questions that actually made this whole endeavor challenging. And this is now where we come to the concept of an actual register. A register, so when we define this in the general setting, this category, we have, we define what, we have defined these pre-registers, which are functions that map updates to updates, and registers are a subset of the pre-registers, and they have to satisfy a number of conditions. So first is that if F and G are registers, then their composition is a register. So that's very important because this will allow us to compose registers together. So for example, if Q is a register from, let's say, C to the 4, so a 2-qubit system, to some big memory M, and first, okay, formally it's this. First is a register that corresponds to, from 2 qubits, the first qubit. So this we could model in this form. So we can take this thing here also as our overall memory, and then ask, inside this, could we have another register like seen as part of this big memory? And if we do that, then we could say something like, I want Q, and inside Q, I want first. And this we can describe in our formalism by saying, okay, then if you apply something on Q first, you take what you apply, you first, so you have some unitary, then you apply first, this gives you a unitary prime, so on 1 qubit, on 2 qubits, and then with Q, it gives you another unitary on the whole memory. So so we have that we can write this composition of registers just by composing them, as long as our category has this law. Then another important law is that f of A times B must be f of A times f of B, because doing 2 updates on a variable and then seeing how this affects the whole memory should be the same as doing the 1 update to the whole memory and then the 2nd update to the whole memory. So these are the 2 most important properties, and we also need that doing nothing on the variable is the same as doing nothing on the whole memory. And we are free to choose additional restrictions on the set of registers. So in the general case, all we need to do is specify some subset of all the pre-registers that has at least these properties. So in the quantum case, it would be those linear maps with FAB being f of A times f of B, and f of identity being the identity. And the fact that the composition of 2 such maps is again a register is something one can check elementary. So what do we have now? Now we have a definition. So if we look, for example, just at the quantum case, we have a definition of what a register is. We say a register is a linear map. Oh, sorry, I forgot one condition. Additionally, if I apply a register to some matrix, dagger should be the same as this thing. This will make it well behaved later. And actually, for those familiar with algebra, this is actually just called a unital star homomorphism. Okay, so what we have now is a theory that allows us to specify quantum registers. Okay? Quantum register is any such linear map from the space of updates on the registers type to the space of updates on the whole memory. We can compose several registers together by like nesting them. So if we have our whole memory M, and we have now in this some register X, and inside X, when we see this as a whole memory, we have another register Y, we can write just X dot Y, or also just X after Y, to refer to Y inside M. So this gives us, solves already one of the problems I mentioned above, namely the this thing. Yeah, I can now, if I have X to be a big variable, I can refer to the first bit or the first qubit of X. I haven't shown you this in the classical setting, what the registers and pre-registers are, but one can do the same thing in the classical setting. But one thing is still missing in this formalism. Namely, what is missing is here this operation. So I want to be able to take two registers and put them together and say, this is also a register, and I can treat it as one unit. And this I call pairing. And in order to enable pairing, we need to be a bit careful. Because bad examples of pairing would be something like if I have a quantum register Q and I try to make the register that contains Q twice. Doesn't make any sense because I cannot, I mean, for example, if I say I want to apply the unitary, I want to apply Hadamard tensor identity to Q tensor Q, what does it even mean? Like what's applied? Like I have only one Q, I cannot double it. But even classically, something like X comma X would not be sensible, because what if I say I assign 1 comma 2 to X comma X? Is this meaningful? Probably not. But how can we see that? I mean, in this case, it's pretty obvious because it's the same register, and we could say, okay, same register, we cannot just assign like pair with itself. But what if these are two different registers? How can we tell whether we are allowed to compose them or when we are not allowed to compose them as a pair? So what we need is a concept of compatibility. So we want to say that if two registers Q and R are compatible, then we can make the pair of them that contains then we can pair them, and this is a well-defined register. And if they're not compatible, then pairing is not well-defined. So how can we define compatibility? Do we have to define it specifically in the quantum setting or the classical setting individually? Can we give a definition in the generic setting? And the answer is yes, we actually can. So in the generic setting, I say Q and R are compatible if and only if for all updates A and B done in Q and R, we have that QA multiplied with RB is the same as RB multiplied with QA. What does that mean intuitively? Intuitively, it means two variables are compatible if doing something in one variable and then in the other is the same as doing it in the other first and then in the one. Which really very well captures the idea that these variables are in independent parts of the memory. If operations between those two, on these two variables, do not interfere with each other, then the variables are compatible. And because of this compatibility and pairing, we need one more important axiom in the generic case, namely, for all registers FG, okay, let me put the types of them there. So a register A to some memory, for example, and G with a different type mapping into some memory, such that for all AB, okay, I can just say such that F and G are compatible, there exists a function, let's just call it F comma G, a register Fg from A tensor B to M, such that for all AB we have that F comma G of A tensor B is the same as Fa times GB. So this is the existence axiom. It does not say that it's like, I mean, this does not just say immediately it is useful, but we just require in the general case that this exists and it's a register. And in the quantum setting, this axiom holds. It follows immediately from the properties of the tensor product. So what does that now mean? How can we work with such pairs? Well, let me give you an example. So if we take our quantum circuit from above, QRS, we have the Hadamard here, then maybe we have a C naught here, maybe we have a C naught here. And now the formal meaning of this circuit is that we apply, so if Q, R, and S are compatible registers, then this first operation is just the unitary Q of H. This operation is described by QR, so the pair of QR, applied to the C naught matrix. And the last one is S comma Q applied to the C naught matrix. So we see we do not need any of those shuffling around operations or anything. We only need to once define what QI and S are in our specific setting. So there could be something like QA is defined as A tensor identity. R is defined as identity tensor B tensor identity, and S is defined as identity tensor C, for example. But we do not need to actually do these transformations back and forth and say how we tuple and untouple and swap wires and so on. We can just use these abstract notions to say that a certain matrix is applied to a certain gate. And even better, we do not even need to specify this specific structure, because we could just say we interpret this circuit in some memory, so possibly a larger system that contains many more wires, and maybe not necessarily in this order or whatever. So we apply it in some system, some larger system, and we just say QRS are just three variables in the three registers in that system. We don't say that they are together next to each other. We don't say how they are embedded. They could be even in a transformed basis or whatever. As long as we state that they're compatible, we can do all the reasoning about quantum circuits just using this formalism, which is much more generic than saying we need to have it in this particular form. And it allows us to do certain operations or proofs more easily. So consider the following case. Let's say again we have QRS and maybe other wires. And let's say I look at this thing. And many of you may know that doing these three C knots is the same as just swapping two wires. But if we want to say this about this whole circuit, then what we need to do is we need to do the whole reasoning again and see that C naught tensor identity times C naught tensor identity times C naught tensor identity is the same as swap tensor identity. Again, this is pretty trivial, but again, this is only trivial because they have a concrete representation. And for example, if we would have wires in the middle, then our tensor products would suddenly, let's say they have a wire T here. And now actually writing this down would become ugly. Of course, we all know it works, but if you try to tell this to a theorem prover, you might find it not a very happy endeavor. But if we now look at the register formalism, it becomes very easy, because what we have is this one here is just the pair QR applied to C naught. The second one is RQ applied to C naught. And the third is again QR applied to C naught, just by reading off the semantics of quantum circuits when we use registers. And then we can use simple rewriting laws for registers. I mean, I haven't listed them, but you can find them in the draft, for example, that I linked in the announcement. So RQ of C naught is the same as QR applied to sigma of C naught, where sigma is a register that just swaps two things. I mean, remember, a register can refer to an actual variable, but a register in the generic setting is an operation that maps linear function to linear function. So sigma is the one that it has the property that Fg after sigma is the same as GF. And we can also directly compute what C naught, sigma of C naught is by using the definition of C naught. So this is the same as the matrix C naught prime, which refers to the C naught on 2 qubits, but the other way around. So now we have that it's QR of C naught, QR of C naught prime, QR of C naught. So the whole thing is QR of C naught times C naught prime times C naught. And this is the swap operation. Of course, now we don't get around the necessity to actually do this computation. But now, here we compute really on the C naught matrix, not on something like C naught tensor with things. We have like nicely removed all the registers from the thing and reduced it to a calculation on matrices that are just of the size of the system we are looking at. So this is the same as cure of swap. So we have shown that these three things indeed swap the wires Q and R, without having had to resort to hand-waving arguments like you can insert the tensor products in the right places and the order of wires doesn't matter. In this case, it is completely formal. Of course, since I gave a rough introduction of the whole thing, it may still look like hand-waving, but this calculation can be done basically exactly like this in Isabelle Hall. So I have made an Isabelle Hall formalization of this concept, and I can write this whole reasoning without referring to any tensor products of identities. It's purely this algebraic reason. Yeah, so this modeling you can also then use to define a programming language, and it becomes easier to define an imperative quantum programming language because you do not need anymore to think about how do I access specific parts of the overall memory, because you can just say on the left-hand side of operations or in the measure when defining measurement and so on, we just can put a register, and the register semantics says how it maps to the overall space. So in the paper, I wrote down a very simple language. Maybe let me sketch it very roughly. It had just two commands. It had on Q apply U, and it had if P with no else and then an else branch, just for simplicity, because what it does is it measures with the projector P, and if the measurement succeeds, it just continues. If the measurement fails, it just aborts the program. It's not the most convenient one, but that's because it's like a toy language. And if I want to give semantics of these things, it is very simple. I can just write here QU, and here sorry, this is not a projector. This is let's say a variable R. But here I require that it's a variable for a single qubit. So this corresponds to a measurement in the computational basis. So this would be, the semantics of this would be very simple, this thing. So very easy to write a language. I can use the same formalism to make a Hall logic around it. So I designed a Hall logic around it, and you can write the predicates in the Hall logic, like for example, register X contains cat 0, or register X and Y together are in the following subspace, and so on. Again, you can use the register formalism to lift subspaces on individual registers to say what they do on the whole space. So you can use quantum variables here, quantum registers according to this formalism here as well, to build up the theory and reason about the subsystems without needing to worry about how they are encoded. And the fact that it my claim that this formalism makes things much easier is evidenced by actually how the size of the various formalizations. So for example, the definition of this simplistic language, including the definition of the Hall logic and all the rules that I need. Okay, there are not many rules because it's a very simple language, but it's 46 lines in Isabelle Hall. Using the formalism, I mean, using already existing formalism for linear operations and so on, using the proof that quantum variables, quantum registers have the properties they should have. Defining quantum Hall logic is done in 46 lines, analysis of quantum teleportation in 193 lines, so much less than you would need, I think, if you would try to do this with less convenient variables, and even proving the whole build-up of the theory of the quantum variables is about 200 lines, like the quantum specific part of this formalization. So it can be used like very simply in a theory improving context. Okay, so that is everything I kind of necessarily want to say about it, but I'm happy to answer any questions. I mean, I can stay here like for half an hour more and answer any questions you have. Consider also there's a classical formalism, so you can do the same operations on classical variables as well. What I didn't mention yet is the infinite case. So what I described so far, the way I wrote it down, works only for finite dimensional quantum registers, because a few properties like the tensor product in the infinite dimensional case is much more tricky. But I think that it all works through. I just haven't checked all the proofs yet. You just need to be careful because the tensor product is more limited, and you need to use the exact right definition of what a quantum register is. Turns out the right thing seems to be normal unital star homomorphisms between sets of bounded operators. I'm happy to talk about that too in more detail if you're interested. So ask me anything and I will try to answer it. And thank you for your attention.
Yeah, thank you for the talk. You said you have a paper about it already, or?
Yeah, I mean, I have a draft that I put on my webpage, and I think I linked it in the announcement. If I didn't, I can still do it.
But it's on your website, I can find it there.
No, you cannot. I mean, you need the direct link.
I see. Okay.
Because it's still a draft, I'm still kind of re-updating it. But it's finalized in principle, except I might add more things. So let me quickly check whether it was in the email.
No, I don't remember that it was in the email. I think I.
Oh yeah, it wasn't. Interesting. I thought it was. Well, then let me quickly give you.
No, in the email you only included the link to this talk.
Yeah, I just saw that also myself. I'm not sure why that happened, but we have also this TCS talks overview page. I linked it there, so I'll put it here in the chat now. Once I find the window again. There's the talk. Okay, so we can find the whole paper there.
Yeah.
It's also going to appear as a talk without proceedings at Plan QC, but I haven't I mean, I quite soon will probably make a public ePrint version of it, but it's yeah, there are still a few points that I want to add and so on maybe, but it's almost finished. And if you find any typos, please let me know, of course.
Yeah, okay, thank you.
Any other questions?
One question that is like bubbling in my mind ever since I heard you talk about this is, What was your roughest approach? Because this looks like an imposing, rather streamlined body of ideas, which looks a little bit like as it had rained from the heavens above.
Yes.
What was the first necessity which moved you to do something in this respect?
Yeah.
And what were your crudest first approaches to this?
Yeah. So actually, I started this in the classical setting.
Yeah.
Although motivated by the quantum setting. So the thing is that if you solve it in the classical setting, you get a somewhat more limited theory also for the quantum setting by just saying, once I have found out what a part of a classical memory is, I can just take this thing in superposition. It's not as general as the approach here, because I can't say things like I look at the register on a different basis, but I can do a lot of the operations still. So I was looking at it in the classical setting, and first approaches were, for example, to say that a register is, let's say, X would be seen as a map from the memory to a bijection between the set of all values in the memory and Tx, where Tx is the type of X, so all possible values that X could take, a Cartesian product, something.
Yeah.
Yeah. So this thing is, but then you need things like, well, two variables are actually, two registers are the same if they only differ in how they operate on something. You might try, and then when you compose, but then you still have the question, what if I compose two? How do I map the something from one to the something of the other? So it didn't work out, and I ended up having, like, even defining what it means for two variables to be compatible. The representation of this something did matter somehow. So just doing the restriction of X to the first output does not fully describe X, and so on. So I ended up with like really complicated things that I tried to work out. So I then ended up having like a variable internally is like a tree of these different operations and parts of it and so on. And then you just trace your way through the tree and so on. It all just blew up and became complicated. And then this idea that it's just functions of updates, it kind of just popped up when fighting with these classical things. And then suddenly I found out that the quantum setting is actually easier than the classical setting, surprisingly. So these concepts, yeah, the concepts, these different laws, they're like very natural because they talk about tensor products and so on. The classical setting, you also talk about tensor product then, but it's not clear what would be the tensor product, what are the updates and so on. So it's not a very difficult theory in the quantum, in the classical case either. So there the updates are just relations on the type, and tensor products are products of relations and so on. But it's not like the thing you expect. While in the quantum setting, it's the thing you expect. You expect linear operations to denote updates and so on. While in the classical setting, there's a formalism that is not the one you expect naturally. So in that respect, it's more difficult.